Variational Autoencoder. Variational Autoencoder is a generative model. It is used for reconstructing the original images and also generating new images from latent space. Here the latent space is continuous, so the sample point for example 2, minus 2 might be decoded as image of A4, and also 2.1, minus 2.1 also produces a satisfactory image of A4. But in the case of autoencoders, the latent space is not continuous. So the sample point, for example, 2, minus 2 might be decoded as image of A4, but 2.1, minus 2.1 might not produce a satisfactory image of A4 due to the latent space is not continuous. So it is considered as reconstruction loss of autoencoder. In the previous tutorial, you can learn how to build convolutional autoencoder. Please go through it once. Link is given in the description. Welcome to aiRobott. I am Kishore Kumar Vaja. In this video, we are going to learn how to build variational autoencoder using Keras. We will train this neural network with MNIST dataset of handwritten digits, which has training dataset of 60,000 and test dataset of 10,000 images of grayscale images of size 28 by 28 for the 0 to 9 digits. At the end, using test dataset of 10,000 images, we will reconstruct the digits. Building a variational autoencoder is very easy. It is similar to the autoencoder, but we need to change two parts in the autoencoder. It is encoder and loss function. The encoder. In an autoencoder, each image is mapped directly to one point in the latent space. But in the variational autoencoder, each image is mapped to a multivariate normal distribution around a point in the latent space. This multivariate normal distribution is derived from two vectors. They are mu and log_var. These vectors are encoded by the encoder while the input image is being passed through the encoder, where mu is the mean point of the distribution, log_var is the logarithm of the variance of each dimension. To encode an image into a specific point z in the latent space, the encoder must have to sample this multivariate normal distribution. The decoder will produce similar images from this latent space, point z, and its neighbourhood points. Let's now try to understand mathematically what we need to do to our autoencoder to convert it into a variational autoencoder and thus make it a truly generative model. In order to understand what is multivariate normal distribution, let's start with normal distribution. The normal distribution is a probability distribution. It is characterized by a distinctive bell curve shape. In 1D, one dimension, normal distribution is defined by two variables, mean mu and the variance sigma square. The standard deviation sigma is the square root of the variance. The probability density function f of x of the normal distribution in one dimension is f of x for the normal distribution mu1 sigma square is equal to 1 by square root of 2 pi sigma square into exponential of minus x minus mu whole square by 2 sigma square. Let's see some normal distributions in one dimension for different values of the mean mu and variance sigma square values. If the mean mu is 0 and variance sigma square is 1, the normal distribution in one dimension is like this bell curve shape, and this is also called as the standard normal distribution. At x equal to 0, f of x equal to 0.4. At x equal to 1.1 and minus 1.1, f of x value is 0.2. At x equal to 2.6 and minus 2.6, f of x value is 0. If the mean mu is 0 and variance sigma square is 0.2, The normal distribution in one dimension is like this. At x equal to 0, f of x is equal to 0.9. At x equal to 0.51 minus 0.5, f of x value is 0.6. At x equal to 1.4 and minus 1.4, f of x equal to 0. If the mean mu is 0 and variance sigma square is 5, the normal distribution in one dimension is like this. If the mean mu is minus 2 and variance sigma square is 0.5, the normal distribution in one dimension is like this. We can sample a point z from a normal distribution with mean mu and standard deviation sigma using this equation. Z equal to mu plus sigma into epsilon, where epsilon is sampled from a standard normal distribution. The concept of a normal distribution can be extended to more than one dimension. The probability density function f of x for a general multivariate normal distribution in n dimensions is like this. F of x1, x2, x2, xn is equal to exponential of minus 1 by 2 into x minus mu whole transpose sum inverse of x minus mu by square root of 2 pi to the power of n into magnitude of sum. For a 2D, two dimension, say x1 and x2, the mean vector mu equal to mu1 and mu2 on symmetric covariance matrix sigma equal to sigma 1 square rho sigma 1 into sigma 2 rho sigma 1 into sigma 2 square, where rho is the correlation between the two dimensions x1 and x2. Variational autoencoders assume that there is no correlation between any of the dimensions in the latent space, so that the covariance matrix is diagonal. This means the encoder only needs to map each input to a mean vector and a variance vector, and does not need to worry about covariance between dimensions. We also choose to map to the logarithm of the variance, as this can take any real number in the range minus infinity to infinity, matching the natural output range from a neural network unit, whereas variance values are always positive. To summarize this, the encoder will take each input image and encode it to two vectors, that is mu and log underscore var, which together define a multivariate normal distribution in the latent space. Mu is the mean point of the distribution. Log underscore var is the logarithm of the variance of each dimension. To encode an image into a specific point z in the latent space, we can sample from this distribution. Using this equation, z equal to mu plus sigma into epsilon, where sigma equal to exponential of log underscore var by 2. Sigma equal to exponential of log of sigma gives exponential of 2 into log of sigma by 2. That gives exponential of log sigma square by 2. Epsilon is a point sampled from the standard normal distribution. So mu is the actual point where the image should be placed in the latent space, and epsilon is a random choice of how far away from mu the image would be placed, and this epsilon is scaled by sigma. So why does this small change to the encoder will help? Previously, in the case of autoencoders, the latent space is not continuous, so the point 2, minus 2 might be decoded to a well-formed image of a 4, but the point 2.1, minus 2.1 might not decoded similar image as the point 2, minus 2. Now with this variational autoencoder, if we sample a random point from an area around mu, the decoder must ensure that all points in the same neighbourhood produce very similar images when decoded, so that the reconstruction loss remains small. This is very nice property that ensures that even when we choose a point in the latent space that has never been seen by the decoder, it is likely to decode to an image that is well formed. The loss function. In the case of autoencoders, loss function only consisted of RMSE loss between images and their reconstruction after being passed through the encoder and decoder. This reconstruction loss also appears in a variational autoencoder, but we require one extra component, that is pullback labeler KL divergence. KL divergence is a way of measuring how much one probability distribution differs from another. In a variational autoencoder, we want to measure how different our normal distribution with parameters mu and log underscore varies from the standard normal distribution. In this special case, the KL divergence has the closed form KL underscore loss equal to minus 0.5 into sum of 1 plus log underscore var minus mu square minus exponential of log underscore var. In mathematical notation, KL divergence for normal distribution n mu sigma is minus 1 by 2 sigma of 1 plus log sigma square minus mu square minus sigma square. The sum is taken over all the dimensions in the latent space. KL underscore loss is minimized to 0 when mu equal to 0 and lag underscore var equal to 0 for all dimensions. As these two terms start to differ from 0, the KL underscore loss will increase. In summary, the KL divergence term penalizes the network for encoding observations to mu and log underscore var variables that differ significantly from the parameters of a standard normal distribution, namely mu equal to 0 and log underscore var equal to 0. Why does this addition to the loss function will help? First, we now have a well-defined standard normal distribution that we can use for choosing points in the latent space. If we sample from this distribution, we will get a point that lies within the limits of what a variational autoencoder is used to seeing. Secondly, since this term KL underscore loss tries to force all encoded distributions towards the standard normal distribution, so there is less chance that large gaps will form between point clusters. Instead, the encoder will try to use the space around the origin symmetrically and efficiently. Let's now see how we build this new version of the encoder in Keras.
In this program, we are going to use MNIST handwritten digits dataset. It is a collection of 60,000 training dataset images and 10,000 test dataset images. In order to handle this huge dataset, we have to create modules for the programming simplicity. First, let us create a folder that is Variational Autoencoder Building and Analysis. All the work will be saved in this folder for our project. So it is our project folder. Now we will create a folder named Models for residing all the modules for our project. Now we will write a code for Variational Autoencoder with the module name VAE.py and save in the folder Models. Let's start the code. Importing the required packages. Importing required packages from Keras. This is callbacks module to be created next. Now Variational Autoencoder class constructing with variables instantiation. Variables instantiation. This is building function. The encoder block building. Input function is used to instantiate a Keras tensor. A Keras tensor is a tensor object from the underlying backend TensorFlow that allows us to build a Keras model just by knowing the inputs and outputs of the model. Input underscore diam is 28 into 28 into 1 tensor. Now this is input layer. For loop iterates for 4 convolutional filters with leaky ReLU layers. This will be used in decoder section. Last leaky ReLU layer connects to flatten layer for flattening. Instead of connecting the flattened layer directly to the 2D latent space, we connected it to layers mu and log underscore var. Here model method used for the model that outputs the values of mu and log underscore var for a given input image. Sampling function for a point z equal to mu plus sigma into epsilon. Our model accepts layer, so you need lambda function to make your expression to be a valid layer in Keras. This lambda layer samples a point z in the latent space from the normal distribution defined by the parameters mu and log underscore var. The Keras model that defines the encoder, a model that takes an input image and encodes it into the 2D latent space by sampling a point from the normal distribution defined by mu and log underscore var. The decoder block building. Here input is output of lambda layer, output of this input layer connected to dense layer. nb.product function returns a product of array elements over a given axis. Output of dense layer connected to reshape layer for reshaping the tensors. Output of reshape layer connected to convolutional transpose layer. For loop iterates for 4 convolutional transpose layers on 3 leaky ReLU layers and 1 sigmoid activation function applied. Now the decoder model is built. Now full variational autoencoder model building. This is the compilation function with reconstruction loss and KL divergence loss functions. Compilation. This function for reconstruction loss, root mean squared error loss function for the brighter reconstructed images. The neural network using loss function to compare its predicted output to the actual output. It returns a single number for each observation. If number is greater, the network has performed version for this observation. This function for KL divergence loss. This function for total loss. With this function, reconstruction on KL divergence losses added. This is for Adam optimizer for compilation. Adam optimizer is a stable optimizer. It used for update the weights in the neural network based on the gradient of the loss function. This is for saving output images in a folder, run in that folder VAE, in that folder 001 underscore digits. In this folder, encoder, decoder, and model images will be saved. In this folder, weights will be saved. In this folder, decoded images will be saved. In weights folder, parameter dumps will be saved. Loading weights function from a file. This is training function for the model. Here we have passed input images as both the input and output for training the model. This is image generator function for passing images via folder for training. This is plotting the encoder, decoder and models in the folder which to get these images we have to install GraphViz visualization software from this link graphviz.gitlab.io/download and must be added to path variables. Next we have to create a module named callbacks.py in the same folder models, importing the required packages, custom callbacks class for the model, variables declaration. This function will save output images from the decoder after every batch training completion. This is the wrapper function to create a learning rate scheduler with step decay schedule. For loading MNIST dataset, we will create a module named loaders.py in the same folder models, importing required packages. Here, H5py package is a Pythonic interface to the HDF5 binary data format. It lets you store huge amounts of numerical data and easily manipulate the data from NumPy. For example, you can slice into multi-terabyte datasets stored on disk as if they were real NumPy arrays. Thousands of datasets can be stored in a single file, categorized and tagged however you want. Creating image label loader class for loading images, loading model method, loading MNIST dataset function. Now create a folder or run. In that, create a folder VAE. Now all the required modules ready for building the variational autoencoder. Now start Jupyter Notebook with the name VAE Building Training on MNIST Digits dataset. Let us import the required packages and import the modules from models, that is VAE and loaders. These are the required parameters. Here we have created already VAE folder in the run folder. Using this code, it creates a folder that is 001 underscore digits. In that, these three folders will be created. Those are which images and weights. Now we will load the MNIST dataset using this code and it will be scaled and reshaped. Let us check the training set shape. Print x underscore train dot shape. This is 60,000, 28, 28, 1. It means 60,000 images for training dataset of size 28 by 28 grayscale images. Let us build the architecture for our model using VAE.py module. Let's design architecture. Here the input dimension is 28 by 28 by 1. That means our image, the grayscale image size. Next, 4 convolutional filters for the encoder and 4 kernels for that filters and 4 strides for encoder. Similarly, for decoder, 4 convolutional transpose layers and 4 kernels for convolutional transpose layers and 4 strides, and latent space is 2. Saving encoder, decoder and model architecture images in which folder? First run this code. Please see once the folder which here encoder, decoder and model architecture images saved with the help of GraphViz visualization software. We can also get this architecture by running Keras summary function like this: VAE.encoder.summary. This is encoder summary. This is decoder summary. This is model summary. Training. Now we will train our network. In the code, the last function for a variational autoencoder is simply the addition of reconstruction loss and KL divergence loss term. We weight the reconstruction loss with a term R underscore loss underscore factor that ensures that it is well balanced with the KL divergence loss. If we weight the reconstruction loss too heavily, the KL loss will not have the desired regulatory effect, and we will see the same problems that we experienced with the plain autoencoder. If the weighting the term is too small, the KL divergence loss will dominate and the reconstructed images will be poor. This weighting term is one of the parameters to tune when you are training your variational autoencoder. Here, R loss factor given the value 1000. Combining the model with the learning rate and reconstruction loss factor. Here batch size is equal to 32, means for every batch 32 images passed to network. Epochs 10 given. 60,000 images were seen to network for every epoch. Print every number of batches, that is 100 here. After passing every 100 batches of images to network, our encoder will produce one new image. It is saved in the images folder. Initial epoch starts from 0. Now the training starts with the training images. all the 60,000 images shown to autoencoder for one epoch. So 60,000 by 32, that gives 1875 batches. For every 100 batches of images, total 19 new images produced for one epoch. Therefore, for 10 epochs, 190 new images produced.
From this output, reconstruction loss is 42.9317 and KL loss is 4.7517 and total loss 47.6833. Analysis of the variational autoencoder. Let's analyze our variational autoencoder architecture. Let us now load the model from the run folder as the output of model saved here. Reconstructing original images. Let us test our variational autoencoder and we'll get reconstructed images. Randomly chosen 10 testing dataset images. Passed to encoder for latent space points. Reconstructing images from latent space points. Now see the plotting diagram for the outputs for input images, for viewing latent space points, for reconstructing images. This is the output. First row is input images, second row is latent space points, and third row is our reconstructed images from latent points. Let's see the viewpoints in the latent space. 5000 viewpoints to be selected for latent space. Here is the output. The black dots are the mu values of each encoded image, the new generated images. Now let us choose 15 points from latent space for reconstructing the images, plotting the latent space points in black color, choosing random points from latent space, reconstructing images, plotting chosen points in red color, plotting the input images, latent space points visual representation, plotting reconstructed images. The black dots show the mu values of each encoded image. Red dots are the samples from the standard normal distribution to generate new points in the space to be decoded. There are not so many generated digits that are badly formed, since the latent space is now locally continuous due to fact that the encoder is now stochastic rather than deterministic. If you run again and again, it will generate new images from these new points. Let's now coloring these new black dots according to the digits, and we will plot the space transformed into p-values. Let us take 5000 viewpoints. A normal cumulative distribution function CDF will return the percentage of the normal distribution function that is less than or equal to random variable specified. Plotting new points colored by digits. Plotting p-value points. Here is the complete plots. The p-value, that is probability value, is the probability of obtaining test results at least as extreme as the result actually observed during the test. The first image is the colored viewpoints in the latent space according to digits. We can see that there is no preferential treatment of any one type. The right-hand plot shows the space transformed into p-values, that is probability values, and we can see that each color is approximately equally represented. Again, it is important to remember that the labels were not used at all during training. The variational autoencoder has learned the various forms of digits by itself in order to help minimize reconstruction loss. Let us now reconstruct the images from these colored viewpoints and we'll see the quality of our variational autoencoder. This is the code. PPF stands for percent point function. It is inverse of CDF, that is cumulative distribution function. This is the plot. Here the reconstruction loss is minimized. So our variational autoencoder reconstructed images are clearer than the autoencoder and the space is continuous. So the neighborhood points also constructed similar images. So far, all of our work on autoencoders and variational autoencoders has been limited to a latent space with two dimensions. This has helped us to visualize the inner workings of a variational autoencoder and understand why the small tweaks that we made to the architecture of the autoencoder help transform it into a more powerful class of network that can be used for generative modeling. In the next tutorial, we will see amazing things by the variational autoencoder by increasing the latent space dimensionality from two-dimensional to multidimensional space to generate celebrity faces. How to generate faces using variational autoencoder using Keras. Bye bye. See you all again. Signing off. Kishore Kumar Vajja from aiRobott.